What is life? Most definitions of life include the descriptive lists of what life does. Life reproduces, life shows metabolism, homeostasis, life is capable of evolving, that kind of thing. But these are just secondary consequences. They're emergent properties. They're what life does, not what life is. There are definitions of life that seem to be quite consistent, quite good, but they depend on longer term processes such as heredity, passing the information between generations, or evolution. But these are to do with groups of individuals over generations. They're processes that happen over generations. They say very little about the state of being alive in the moment, the instantaneous state of being alive. That's what's interesting for us today. So in my peer-reviewed paper, I presented a mechanistic definition, one rooted in the physics and chemistry that distinguishes living and non-living things. And why not? Living things are made of matter, they're made of atoms and molecules. And we're now armed with the tools to investigate down at that scale of matter. We can see atoms, we can see single atoms, we can visualize them, we can look at molecules within cells, biological molecules, working in real time. So this is not some kind of mysterious realm that's outside our sphere of investigation, and we can do this. In fact, we have. This line of thought goes back to physicist Erwin Schrödinger, who pointed out that life is unusual because it's characterized by creating order, by creating structure in a universe that tends towards disorder. So life fundamentally creates order, creates structure. What Schrödinger was a bit less precise on, due to the knowledge available to him at that time, was how precisely life does this. Now, of course, in cells, us biologists know very well that there is just a bewildering array of different molecules, and at least if you consider them as static textbook images, it doesn't look like they have one single thing in common. But of course, they're not static. They're not just sitting there doing nothing. They're moving. There's constant motion. And actually, they do share one thing in common, and that's how they move. They move with a very particular kind of motion. To understand this, it's important to recognize a basic premise in physics, that down at the extremely small scale of atoms and molecules, everything is in constant motion. Molecules jiggle constantly. We measure it as temperature, the molecules jiggling around, banging into our thermometer, but usually this movement is futile. It happens in random directions, and so it doesn't do anything. As we scale up these motions for millions of molecules making up a single rock, the tiny motions of the different molecules average out, which is why at the macroscopic scale we don't see rocks jumping around on their own, but their component atoms and molecules are continuously moving, vibrating, jiggling in place. A similar thing happens in living cells. Their molecules have a temperature and are jiggling. And within each cell there are literally millions of components, and they're all jiggling. But key biological molecules, the ones that do the work, don't just jiggle randomly. Due to the peculiarities of their structure, the jiggling makes them repeatedly change shape or conformation, and they do this repeatedly and cyclically along a single plane of action, either in a linear plane or spinning along a plane. These controlled cyclic shape changes mean that the molecules have a greater probability of moving along in one particular direction or spinning in place and doing work. So this is what does the work inside cells. This is what drives metabolism. In non-living systems, the molecules aren't shaped in a way that lets them do this. They just jiggle in place. So the molecules in both rocks and cells jiggle, but in rocks, this jiggling, this movement is random and directionless, and in cells the motion is directed and can be used to pull and move things around, or to force molecules together, to force them apart, to catalyze reactions within cells, to do things for metabolism. And to do this again and again in a dependable way. Now, if you're a biology student, you'll have spent months learning about the bewildering array of molecules within cells, but the ones that do things, and I'm talking about motor proteins, ribosomes, enzymes, and in particular enzymes such as ATP synthase, ATPase, RNA polymerase, they all share this property of uniplanar conformation changes, changing shape mainly along one plane, that creates a directional motion crucial to their function. These molecules function as so-called heat engines. They exploit thermodynamic gradients, differences in energy, and they transform this random thermal energy or movement, agitation, into reliable motion. These thermodynamic gradients are either direct, so a difference across a membrane, or they're indirect, in which a transmembrane potential creates a carrier molecule such as adenosine triphosphate or guanosine triphosphate, which then diffuse within the cell, encounter a working molecule, and can induce a thermodynamic gradient across it to activate motion. Inside every cell, millions of these heat engines are working constantly, driving metabolism, growth, repair, all of the processes that happen within the cell to keep it alive. But a single molecule is not alive. The thing that's alive is the network together. All of these molecules in a self-regulating network. And it's this coordinated activity that keeps an organism alive from one second to the next. So here's the definition of life from my peer-reviewed paper, which you can find a link to in the description. Here it is. Life is a self-regulating process whereby matter undergoes cyclic, uniplanar conformation state changes that convert thermodynamic disequilibria into directed motion, performing work that locally reduces entropy. In simpler terms, life is powered by networks of molecular machines that convert random thermal energy and energy gradients into directed work that creates structure. This definition also helps create a clear boundary. Living things are networks of heat engines that reduce entropy by doing work, creating structure. Non-living things, like crystals or fire, may look organized, the crystal looks organized, but they don't have molecular engines creating the structure and driving the processes that make them. Even prions, which are biological molecules, even prions don't use networks of heat engines to create structure. They seem to reproduce, but actually they multiply by inducing damage, a cascade of damage in other prion proteins. So it's not true replication and reproduction, it's inducing damage, so they seem to reproduce. But this actually creates increasing disorder, not increasing order, which Schrödinger said is one of the prerequisites for recognizing life. So prions are not alive, okay? It's not the single molecule, and the process of life involves creating structure, not destroying it. So prions are not alive. The new definition also makes sense of borderline cases like viruses. Outside a host, viruses are inert, and inside a host cell, they join in the living network of that cell, so they become alive in a way. So we can go beyond the argument of are viruses alive or not. It depends on where they are, where they find themselves. In some circumstances, they're not. They're just inert molecules. But when they find themselves inside cells, they join life. They become alive in a way. So they really are a borderline case. I know it sounds like a weird and possibly unsatisfactory solution, but the answer to that question was always going to be weird. Why is this important? First, it gives us a mechanistic definition, one based on a single physical principle rather than a vague list of traits. Secondly, it's universal. It doesn't depend on any particular molecule, such as DNA or even proteins. So it doesn't actually depend on Earth chemistry. Any autonomous, self-governing network of molecules could potentially be alive. And when we're searching for life on other planetary bodies, that's what we should look for, not necessarily DNA or proteins or even water, but molecules that repeatedly change their conformation shape in one plane to do work together and regulate each other. And this should happen inside a liquid medium which is thermally agitated. So it doesn't necessarily rely on water, but it could be any kind of liquid system. And third, it ties in with how we consider life and death in medicine and legal definitions of death, for example. Life ends when these networks fail, such as when networks within the brain or within the heart fail. So a heart can be alive even though living systems have failed in other parts of the body. It's alive, and that's why we can transplant it even though the brain is dead and the person is considered dead, but the heart is still alive because those reaction networks, those networks of heat engines within the cells are still running. To conclude, life really is best understood as animate matter. It's powered by countless tiny molecular heat engines that continuously convert energy into directed motion, working against entropy. That's what makes organisms alive in the moment, from one moment to the next, in the instantaneous sense of being alive. And as these simple thermodynamic processes are literally universal, this is probably the hallmark of life wherever it exists. If you want an extended explanation with diagrams and videos and the original scientific literature, the citations that support what I'm saying, or if you're interested in the implications of life for biological life, for artificial life, or for searching for and identifying life on other planetary bodies, you'll find links in the description to a much longer video presentation with the cited scientific literature and the detailed arguments laid out in the peer-reviewed paper itself. Thank you very much.